Good day, welcome back. And I believe you are all revising the previous day's sessions and you are getting familiar with the Cortex M4 series of different registers, different peripherals. And I believe you would have gone through by now the functional block diagram, so you are familiar about the different bus systems, etc. If not, please go back, watch the videos, and revise yourself so you'll get more in-depth knowledge. Today is day 8 and please welcome back and let's get in to see what day 8 unfolds for us. Today we're going to learn about memory map and bus interface of Cortex MX processor. What are all the things that's involved in memory map and what are all involved in bus interface? That's we're going to learn today. So these are all the sections we will cover. Memory map, so how and where memory map is used and what is its values and its address, and the microcontroller bus interface, what are all the different bus interfaces that you will be using, the advanced high performance bus and advanced peripheral bus. Likewise, so you will be learning what buses are there in Cortex M4. And the next one is the MCU clock, the microcontroller clock. There are different types of clocks, and you will be learning about what they are. So let's get in and learn today. Before moving in, I would like to give you a short introduction about whom I am representing. I am representing A2DG, as you can see. It's a startup company by Anbukarasu brothers. My brother Alex and myself Arul started in 2023. Both of us have 20 plus years of experience working in the industry, and we would really like to share our experience and our knowledge to you all so that it will be helpful to you to shape up and be a better professional engineer in the end. Our mission is to convey our shared experience and knowledge to at least 100,000 future professionals out there through our online courses. The one big advantage is you can do this study at your own pace, at your own time, wherever you are. So that's really good. About me, I am Arul Prakash Anbukarasu. You can call me as Arul or APA, as popularly as I would like to be. Okay, jokes apart. I have 20 plus years of experience working in Australia. I came here back in 2003 and did my master's majoring in embedded systems, VLSI in project management. Since then, I've been working here concentrating on major industries, mainly in renewable energy sector that's dealt with solar and wind, power systems that dealt with lead acid batteries. Then there is the network embedded systems where the automatic teller machines, the teller cash registers, point of sales, those are all the network embedded systems that I have hands-on worked almost all the embedded development lifecycle in each and every company, and banking automation systems and smart parking operations. So my main expertise is on all the three: embedded systems, VLSI, and project management. This is what I would like to share with you, my experience and my journey, how I went about, so that you will learn in an easy way. You don't have to do the hard way by trying it all by yourself, but through my teaching it will get you into that first step in the ladder, and you can climb very soon. I got a small announcement to make. I have categorized into two different categories. There is the YouTube viewers and the internship professionals. The YouTube viewers, all the video sessions that I'm handling now, I'll be loading into my A2DG YouTube channel. You please go there and watch all the videos. In order to be eligible to get a E certificate, you have to attend at least 28 classes, and that gets you an E certificate. But due to some regulations from YouTube, the videos can't live there forever, so it has to be removed after 2 or 3 days. So if you miss a day, you can't go back and revise or catch up. So that's the drawback. So please, I would advise strongly and I would recommend you to join our internship program. By joining our internship program, it will get you and acquire your internship certificates, and that's worth a lot. I give this example. So when you go into the interview, or when once you got the job, first job, and you are in the industry working with the team, your knowledge and your experience will sit among the top. So no one in the industry need to give you prior teaching learning experience in there, because you spend this 30 days and you learned everything. So you will be ready to go whatever project you will face in the industry. So the senior engineers and the managers will be so thankful that you already done this. So it reduces their part a bit. Not only that, you will get a separate login to only access to you through our learning management system portal. You can log in and you can go through our daily session, and once you finish you have to click complete and continue, and that will cover as your attendance for that day or for that session. Not only that, you can access to all the course contents unlimited. So anytime, anywhere, you can go back again and you can revise and recap. You can read it and rewatch it. And also the course contents, it's unlimited. You can pause it, you can rewind, or you can fast forward, you can come back, do all sorts of things. Also, if you got stuck somewhere in the middle, please contact our backend team and they would be able to help you to move you along through the course. And these are all the materials required for learning. Hands-on experience is the key here. So the more you practice, so the more you have your hands on the hardware, the more experience, more knowledge you will gain. So please contact Pantech Solutions down there, and they are the manufacturing company, and they would be able to assist you to acquire all of this. So you need to have all of this to learn this Cortex M4 series. Also, after you finish learning, you can use all of this and you can create your own projects, you can create your own design. So it is a worthy investment, which doesn't stop here. You can take it to other projects as well. So please, the investment that you're going to make today will help you for your future. So please go ahead and contact Pantech Solutions and they would be able to help you to acquire all of that. Today it's going to be a bit of a theoretical, and I'm going to explain the program, just a short program to show what it is. To go through with me, you need all these 5 documents. What it is, it's the STM32F411 datasheet that I referred to you yesterday or the day before the sessions, an STM32F411 reference manual, and the schematics when you learned about the blinking LED and controlling the switch. I sent you links. When you go there, you can download the schematics links. And the new thing is you need to download Nucleo user manual, and I'm going to refer that to another microcontroller from Texas Instruments to compare between the STM32 and the Texas Instruments microcontrollers. So if you haven't got any of this, please download, and it will be really helpful to go through with me. So please have all these documents handy. I'm sure you are keen like me to get into explore what these are all about. So let's get going, not to waste any time. So let's get in. Before giving you elaborate explanation, I would like to start today from a basic architecture. You would have learned this through your engineering curriculum over the years, but I'm just recapping for you. Any microcontroller that you are using or you used or you're going to use will be in under one of these 2 architectures. So this is the basic architecture. As you maybe also know the name von Neumann and Harvard. What is the difference between the 2, von Neumann and Harvard? In von Neumann architecture, the CPU, the arithmetic logic unit, the control unit, the registers, they are all connected via the same bus to both the data memory RAM and the program memory ROM. What this limits is, if you want to say you want to get data from or fetch an instruction at program memory, and also at the same time if you want to get to data memory, you can't do that. You can either get data memory or you can get program memory, whereas the Harvard is really versatile. So all the CPU, ALU, CU in Harvard architecture connect to the data memory and program memory on a different bus. In other words, if you want to simultaneously fetch something from the data memory and also from program memory, you can do so with only Harvard architecture. So that's why this is a much preferred architecture, because you can do multiple things, whereas one Newman you can't, because this slows down the process because you keep using the same bus, so there will be a network traffic in there. So the architecture that we learning in this series is STM32F411, and that is based on Harvard architecture. So I thought to give you a touch base in regards to architecture, so it would help you to learn the basic difference. So when you go to writing your own program, then these things will come to your mind and you would be able to easily understand and write your codes. So let's get into the memory map of the microcontroller unit, the STM32F411. That's the microcontroller that we are using. It's based on ARM Cortex M4 processor. So it has the basic architecture with the processor is STM32F411. The board that I showed you the other class is STM32F411 nuclear board, and the architecture we are using is the ARM Cortex M4. And the width of the system bus is 32 bits. As you learned yesterday, these are the 32 bits. So what that is, you can access to 2 power 32 different addresses. So that will take you to 4 gigabytes of different addresses that you can access. So the range of addresses for this memory map would start from 0000 0000 to FFFF. So this is the range of address for any memory map. So be it a flash memory or static RAM, anything, everything will have its unique address. So you need to go to the memory map to follow that. Before going to the memory map, I would like to highlight with you about the functional block diagram, so you will have a better understanding about the various peripherals for a start. As I said earlier in the previous classes, so the functional block diagram lives in STM32F411 datasheet on page 15. This is the functional block diagram. If you downloaded the manual, the datasheet, this is the one you'll get. And if you zoom in to that part, that's the one we're going to learn about today, and this is what you will see. So this is the memory section, and this is the bus section. So this is the one we're going to learn about today. I will show you from the data sheet itself. Just one moment. I'll go to data sheet and going to page 15. So this is the functional block diagram as you would have downloaded already, and you would come to this, and this is the one we already knew earlier, so this is the one I'm going to show you again. So we are talking about the bus interface and the memory map today. So the bus interface is connected. If you want to connect to the peripherals, microcontroller is all about connecting with peripherals. So when you want to communicate, you need to have a peripheral. With the help of the peripheral, you can communicate and talk to the other devices. So likewise, the peripherals and everything will be connected via a bus. So the ports also are connected via a bus. And ARM Cortex M4 runs on 100 megahertz. What that 100 megahertz is the operating frequency. So every microcontroller, again you have to refer the data sheet, will have its operating frequency. Operating frequency is the bus frequency. So ARM Cortex M4 that we are learning throughout now runs on 100 megahertz. And this ARM microcontroller is connected to the AHB bus matrix. The AHB bus matrix is, AHB stands for Advanced High Performance Bus Matrix, and if you dig deep into that, it's connected to AHB1, Advanced Bus High Performance Bus 1, and if you still dig deep into that, the Advanced High B1 is connected to what you see is two divisions. So this is called a bridge. You can call as a bridge circuit or a bridge bus, where it divides into two different sections. So this is where it concentrates on high speed and low speed peripherals. So if you want to use anything high speed peripherals, then you have to go to APB2, which is Advanced Peripheral 2, and that runs on 100 megahertz speed. And if you want to do anything on a lower frequency, then APB1 is a 50 megahertz. So these are the low frequency bus. For example, if you want to program for an USART or SP2 or I2C3, then you got to enable the APB1 first and then write programs accordingly to the registers. Whereas if you want to access to all the ports that you learned from the previous sessions to blink an LED and control the switch, then you need to come to the AHB1 and you need to enable that clock. And also moving to here, it has every microcontroller has the clock. Without clock, it's very it's hard to program. So clock is the one which connects with all the peripherals, and it synchronizes with each and every peripherals with the help of clock. So there is a circuitry which has provide all the clocks. So the H clock that comes out, that goes into the AHB bus clock. The APB2 clock and APB1, they are the peripheral bus clocks. So for these two peripherals, and AHB-B1 P clock and AHB-B2, they are all for the high performance. AHB1 and AHB2 is for those. So this is about the bus peripherals. As you can see, if you want to interface high speed sensors, then you need to choose APB2, or if you want to interface with low speed, then APB1 runs on a 50 megahertz. For example, if you want to use a USB in your program, if you want to write code, then that means you can't access AHB1. It is connected directly to AHB2 and it runs again on 100 megahertz. So you need to enable this bus so that you tell the microcontroller that it's coming through the AHB2 bus. And when we talk about the memory mapping, you can see here there is three different buses. ARM Cortex M4 has three different buses. What are they? They are the D bus, I bus, and S bus. D bus is nothing but data bus. I bus is nothing but instruction bus. S bus is nothing but system bus. If you want to access to flash memory, then you can access via both the data bus and instruction bus. You can't access to flash memory via a system bus. It's not connected. But if you want to access to instructions set on the static RAM, then it can be connected through the system bus. You can't access the instruction via the data bus and I bus on the SRAM. Whereas for flash, these two buses are used. So these are all the different bus architecture here that is showed. The direct memory access is connected via the direct AHB bus matrix, and this is the USB, and as you can see, the timers are connected to APB1, and the CRC cyclic redundancy check is connected to HB1, all the ports connected to HB1. And if you want to write a program for ADC or SPI, use our timer 9, 10 and 11, then you have to use APB2. So as you learned yesterday or the other day with previous sessions, if you want to concentrate to write one program, then the first thing is you have to enable the peripheral clock. That is a must, because it synchronizes with all the other peripherals and tells a microcontroller where it's coming from. So that's the key here. Okay, let's get back to our session. Now let's get into detailed system architecture. So this is the bus architecture that we just discussed earlier. This AHB advanced high bus peripheral, the bus matrix. This is the one we are going to see in depth in the next one. So all these yellow colored ones, they are the master devices. So the Cortex M4, you have the Ethernet master, you have the high-speed USB 2, you got the dual port and direct memory access, you got the dual port direct memory access 2. And these are all the green ones denotes the slave addresses or the slave devices. The AHB1, AHB2, static RAM 2, FSMC, which stands for flexible static memory controller, and the that's the external memory. This is the internal memory, which is a flash, and the flash is connected via the bus matrix. The blue dot represents there is a connection access from master to system, slave. And if you don't have the blue dots, then that means the master via that line can't be communicated to the slave. For example, we are learning Cortex M4 architecture. So if you take, for example, the D bus, the data bus, that's the first one. If you want to access any data from SRAM or SRAM2 or external memory, you can use the D bus, and you can connect and fetch data from these three. So also to the flash memory. Whereas if you take the system bus in here, you can't access the flash memory by using a system bus. You can only access to the external memory and the SRAM ones. So likewise, if you want to use the high-speed USB, then you need to use the USB, and you can only access to SRAMs and the external memory. And the direct memory access, you can access to almost all through these two lines. And this is the one we saw there. The AHB1 advanced high performance bus is connected to a bridge, and the bridge is connected to differentiate between the high speed frequency and the low speed frequency, with the dual port advanced peripheral bus 2 and advanced peripheral bus 1, where different parts of the peripherals are connected. So this is how the bus matrix is linked with our Cortex M4. Then we learn about the memory map. So every memory port or peripheral, every peripheral will have a memory address. It's called a boundary address. Boundary address is nothing but boundary, as in general, when you say boundary, it is a limit. If you take a LAN, then you have the starting point and the end point, and that's the boundary between the start and the end. Likewise, in the memory, you have the starting address of 400 to 000 if you want to use port A. Then if you want to use port D, then that's the address 044400 to 0C00 or 0 to 402. So I'll show you in the reference manual, so you will have a better understanding. Reference manual, I'm going to memory mapping to page 37. So this is the memory map we just saw. If you want to use port A, then the memory map address, the base address starts from 4002 to 4023FF. Likewise, if you want to use I2C, then the memory address is 4000 to 5400, and for an ADC the memory address is 4001 2000. So this is the memory map that is in the reference manual on page 37. If you go there, please read yourselves, and you will have a better understanding when you come here and read. So that's the boundary addresses for each and every memory map. And this is the continuation of the memory map which I just showed you with different peripherals like I2C, USART, and timers. Every peripheral will have a starting address I should say, and an ending address. That's that. The regions of the memory map details. So when you say the code, the instruction fetches and performed over the I code, the instruction code, and the data accessed via the D code, the D bus code. SRAM instruction fetches and data accesses are performed over the system bus. Likewise, the peripheral instruction fetches and data access by the system bus. If you want to access external RAM, then the instruction fetches and data access are performed by the system bus. You can't use data bus or instruction bus. So these are all the memory map that from the table, from this reference table. If you want to see what is the base address of AHB bus 1 peripherals, it is 04000240. For GPIO, it is 400240. For RCC, reset control clock register, the boundary address is, or base address is 40023800. APB1, it's 400000. For a flash internal memory, it's 080040. SRAM, it's 20000400, and the ADC register is 040012000. Again, if you go here to the memory access, memory map, and this is where you will get for GPIO port A, that's the address. And likewise for ADC that you just learn, 4001022000. So likewise every peripherals, HB1, HB2, APB2, APB1, everything will have a boundary address. So that's what it's saying in this memory map. So let's get into see what the flash memory interface connections looks like. As you can see, this is the, if you go to the reference manual on page 42, this is the diagram you will see on page 42. If you scroll further down, so this is the diagram I put there in the presentation. As you can see, if you want to access the flash memory, you can access via the I code and the D code. The microcontroller can communicate via the instruction bus and the data bus, and if you want to especially connect to the flash memory, you can do so by the instruction bus and the data bus, but you can't use a system bus to access to flash memory. But if you want to access SRAM and AHB peripheral 1, then you have to use the system bus to get to SRAM, whereas the system bus can't access to flash memory. So that's the flash memory interface connection inside the architecture. So this is how you have to remember when you want to write a program for the memory concepts, memory interface connection. I got a small program to explain to you about the bus interface. Program to interface a bus interface. In any C program, when you use a const int data equal to 10, this is a initialized global memory value. And because being it's initialized, it can't be changed. So that's why we are using on const. and those memories are stored in the flash memory, which is the internal flash, and it can't be changed. Whereas if you create data 1, meaning it's uninitialized, you can store it in the RAM memory, the external, because this can be changed, so that's why it's stored in the RAM and you can access anytime to it. And in the main program, when you say data 1 equal to data, this means the data loads from the flash and moves to the SRAM memory. So that's what this line meaning is. So if it is a global memory, if it is initialized memory, it will be stored in flash. If it is uninitialized memory, then it will be stored in RAM, because the values can be changed. That's the basic of it. So if you get into the bus interface, how it is connected to the I bus and the D bus, ARM Cortex M4 connects to the flash internal structure via the I bus and the D bus, the instruction bus and the D bus. The instruction bus is connected to get information from the instructions inside the flash. The D bus will be connected to inside flash to get constant data. And also internal flash will have vector tables. You will learn about vector tables in the further session, but this is the internal flash architecture, if you like. Inside the flash, these three will be there: instructions, constant data, and vector tables. And this is how you communicate with the microcontroller through instruction bus and data bus. So if your instructions are present in the memory locations of 000, 0000 to FFF, FFFC, then your processor will fetch the instruction using the I code, the instruction bus. Whereas if it is outside this memory address that's mentioned there, then if you want to fetch the instruction, you have to use a system bus. For instance, if your data are present in the memory locations of 000, 000 to 1 FFF, FFFC, the processor will fetch the data using the D code, the D bus, data bus. But if it is outside this memory location, then you need to use a system bus to fetch the data. So that's the bus interface. Now let's see the high speed versus low speed. As you saw earlier from the functional block diagram, the functional block diagram, the AHB bus matrix is connected to a bridge circuit or a bridge unit or circuitry, if you like, and that divides the high speed versus low speed. So you have to, as a programmer, as a system engineer or a software embedded engineer, it's your responsibility to check the data sheet whether you are programming for a high speed peripheral or a low speed peripheral. So if you use the high speed peripheral, then you have to choose APB2, and that runs on 100 megahertz. And say, for example, if you want to write a program for communicating with USART1, then that's connected to the APB2. Whereas if you want to write a program for SPI and I2C2, then that's connected to APB1 on a lower frequency speed. So you have to use APB1. So that's you need to be aware of what peripherals that you're going to communicate to. So you understand the bus speed, so then you come here and then see whether you have to use high speed or a low speed. So please keep that in mind, and this functional block diagram always you have to check before you jump into writing the code. So this is about the high speed and low speed peripherals bus interface. I think I could give you a short break, and when you come back, I will show another microcontroller just to give you an example and compare with ARM Cortex M4. So please go and enjoy that break. I will see you back in shortly.